In this video, you're going to be learning about what a half-life is. We're going to be looking at some conceptual methods of calculation. And then lastly, we're going to be taking a look at a half-life equation and then applying that to a couple different problems. For number one, we have tritium that has a half-life 12.3 years. How much of a 40-gram sample is left after 36.9 years? So first of all, let's go ahead and cover what a half-life is. It is exactly what it sounds like. It is an amount of time. It's the time it takes for the initial mass to decay down to half its mass. Now, for these three different elements that we have tritium for number one, we have carbon 14 for number two, and we have gold 198. So when we're talking about half-life, we're talking about atoms that are unstable, that are going to decay by losing some of its mass. If it's an atom that's completely stable, it wouldn't be a good atom to use for one of these problems because its half-life is either going to be too insanely long or it's nearly infinite. All right, so for number one, we have tritium. It has a half-life of 12.3 years. How much of a 40-gram sample is left after 36.9 years? Now, if we're solving a problem like that, we are looking for a mass. We're looking for a final mass, but we need to figure out how many times we're going to chop that 40-gram mass in half. Now, we have a total time of 36.9 years, and we want to see how many half-lives are going to occur within that time period. So we're going to divide it by 12.3. And we find out that it's 3 half-lives. Now, after that simple bit of math, we now know that the 40-gram sample is going to get chopped in half 3 times. So let's go ahead and do that and see what we get. All right, so we went ahead and took that sample and split it in half 3 times. 40 divided by 2 equals 20. 20 divided by 2 equals 10. And 10 divided by 2 was the third time it was sliced in half. And then we have a final answer of 5 grams. That one is a fairly simple 2-step problem. First part, find out how many half-lives we have. And then secondly, we want to make sure we divide that original number by 2 3 times. All right, number 2, we have a 200-gram sample of carbon 14 has decayed from 200 grams to 12.5 grams. How many half-lives has it undergone, and how much time has elapsed if its half-life is 5,730 years? So for this problem, we know what the final mass is, but we don't know how many half-lives occurred. So all we have to do is do a similar step to we did in blue over here for the first one. We're going to go ahead and start with our 200-gram sample, and then we're going to see how many times we have to cut in half to get to 12.5. All right, after I took 200 and divided by 2 4 different times, that took me to 12.5 grams. So I know that 4 half-lives occurred. So I solved for my first part. Second part is going to be pretty simple. It says how much time has elapsed if its half-life is 5,730 years. So we know that each half-life is 5,730 years, and now we know that 4 of those occurred to get that 200 grams of decay down to 12 and a half. So we have to just multiply this by 4, and that gives us 22,920 years. So that is our final answer for the second part. All right, going to our last one, we have gold 198 is decayed from 50 grams to 1.56 grams over 13.45 days. What is its half life? All right, so we're going to take some pieces from our previous questions and go ahead and work this one out. Again, when you typically have the initial and final mass, you basically just work your way from the initial to final mass to see how many times you're going to have to split that thing in half to get to your final mass. So let's go ahead and do that first. So we use the same method that we did with number two. We took our initial mass, split in half until we reached our final mass. And for this one, we're kind of working a bit backwards. For this final step, for number two over here, we had the time for a half life and then multiplied it by the amount of half lives for the total time. Now we're going in the reverse order. We have the total time, so we're going to have to divide by the amount of half lives to get the amount of time for a single half life. So we had 13.45 days pass by total, and we had five half lives occur. So we're going to go ahead and divide that by 5, and then we get 2.69 days. So for most of these problems, you're not really doing anything too tricky mathematically. If you just kind of work your way through a variety of problems like we did here, you use the same types of methods to figure out a single half-life, total time, final mass, and things of that nature. All right. Now, I typically don't use the equation very much, but I'm going to go ahead and show you the formula and see how it could be applied to a lot of these cases. All right. So let's go ahead and label what these are. So this is your remaining mass. This is your initial mass. And then in our exponent, this is a half-life. And then T is your total time. Now, like I said, I tend not to use this equation because it can be pretty helpful, but a lot of times you can kind of reason your way through the problems as I did before, and the calculations turn out to be fairly easy. All right, so let's go ahead and work out part of 1 and 3 and kind of see how this formula works out. So what we're going to do for number 1 is we can find out how much of the 40 gram sample is left after 36.9 years. I guess it's not part of it. That is the question. So we're going to be solving for the remaining mass. And then we have an initial mass of 40 grams. And then we have 1/2 raised to this power. Total time elapsed 36.9 divided by half life of 12.3, which basically is just 1/2 to the third power. So then you take 40 times, in my calculator I like to put 0.5, it really doesn't matter, raised to the third power, which is 5 grams. So that method did work out pretty nicely for that problem. For number 3, this one doesn't work out quite as nicely, and you'll see why in a moment. So we have the final remaining mass, the 1.56. We have 50 grams to the 1/2 raised to the power of 13.45 divided by the half-life. Now for this one, what we're going to do is a couple things. First, we're going to divide both sides by 50. And then that's going to change our left side to, I'm going to write it over here. So 0.0312. And the other side is 1/2 raised to the same power. All right. Now what you want to do is you want to transform 0.0312 to 1/2 to a certain power. So if you just keep on doing a bit of trial and error, you can find out that 0.0312 is 1/2 to the 5th power. And this side over here is 1/2 to this power. I'll just kind of put an arrow here to be a little bit lazy. All right, so let's clear a little bit of space here. Now, both of these expressions over here are 1/2 to the blank power. The first one is 1/2 to the 5th power. The other one is 1/2 to the 13.45 over the half-life. So those exponents would be equal to each other. So now we set them equal to each other. We can do a easy little cross multiply, and then your answer is basically 13.45 divided by 5. And then you would get t equals 2.69 days, as we did before. Now, that way is, in my opinion, a bit of the ugly version. I kind of like the longer, more simplistic version. I mean, the other way is longer as far as writing more numbers, but really not that long time wise. You're just kind of dividing the number, the initial mass, by 2 a bunch of times, and then doing a tiny bit of math overall after that. So I hope those examples were helpful to you. Thank you for watching and listening.